My name is Neil Morris. I work for CMTG in Perth, Australia. I look after the data center and products like flash system storage.
Right. And I'm Andy Walls. It's great to meet you, Neil. And I retired from IBM about 10 months ago. I was an IBM fellow, CTO for Flash Systems. And since then, I started my own consulting company called The Great Walls of Storage. And now I consult for IBM. And the FCMs and Flash Systems are still extremely important to me. And I thank you, Neil, for you using them and your business using them.
Okay. Andy, everyone's talking about QLC these days, but who actually started shipping it first in enterprise storage systems?
Well, IBM did, and I remember the exact date that we announced it in Stockholm, Sweden. It was February 20th of 2020. And Neil, the reason I can remember that with such precision is that the week after that, I went to the UK for a meeting there at Hursley, and then on my flight home, the world shut down. All right. It was the pandemic. And so we've been shipping QLC ever since the pandemic. So for over 5 years, and we have hundreds of thousands of them sold. And the difference between us and others who are now shipping QLC is this. We ship QLC everywhere. We have the IP through our research and our development to know how and to figure out how to make QLC as reliable, to perform as well, and therefore that's all we ship is QLC, and it allows us to have a density advantage, a power advantage, a cost advantage over others. And plus it's simpler. Instead of you having to say, well, do I need QLC for this or TLC for this? You just buy a flash system and it'll do what you need.
Andy, can you back up a second and explain what QLC really is and why it's such a big deal?
Okay. And I'll try to avoid quantum mechanics as I do that, Neil.
Much appreciated.
QLC stands for quad level cell, 4 bits per cell. All right. And so a client can store 4 bits in every transistor. Well, that means that there are 16 states. All right. So on a voltage range that would go from 0 to about 5 volts, let's say, we have to be able to accurately tell the difference in every bit between 16 different thresholds. All right. Well, a transistor will tend to hold the charge, and so you'll get some shifting, and so that's why QLC has lower write endurance than TLC. However, we've spent a lot of time with the QLC that we use coming up with really innovative ideas that allow us to still get that endurance. For example, we use something called health binning. We don't treat every block the same. We go in and look to see which ones are the healthiest. Those that are healthiest, we write the most data to. And so we get an increase in the average endurance as a result of that. We have several other techniques that allow us to get the endurance. So QLC is 4 bits per cell, TLC is 3 bits per cell, all right? And so you get right there a 30% advantage, but it's really more than that, because being able to fit more bits per cell means that I have die that are bigger. I mean die with more capacity on them. So we can drive more flash that way. That's what QLC is.
Wow. So what makes IBM's FCM different? And why does IBM choose to design and build your own SSDs?
Yeah, it's a great question, because if you're investing in your own SSD, obviously that's taking investment away from other things, right? And so any business, you have to be careful what you invest in. There's a limited amount of money. Back in 2012, actually late 2011, as Flash was really starting to take off, we knew that we needed to acquire a company, and we looked at many of them, and we ended up purchasing Texas Memory Systems in Houston, Texas. Well, they have the skills, they have the know-how, and they were building their own flash controller already. And it's a huge investment to write your own flash translation layer, as we call them, and to fit all that design into an FPGA. Well, they had done it, and we could use that as a base to build off of. And therefore, we use that. Now, if all we were going to do is just have a cheaper SSD than everyone else, that wouldn't be enough, Neil, because let's face it, a company like Samsung and Kioxia and others, they have higher volumes, and that would be tough to just have lower costs. So we went beyond that. We had the idea to put compression inside the FCM. And now the compression then offloads the work of the controller, and we get very good compression ratios. In addition, we use the FCM as a computational storage device. We also collect statistics and things like entropy and things like the delta compression, how the compression changed each time you write it. And that is used for our ransomware detection model that we run on Virtualize. And there are several other things that we do, offloading the processor and the controllers, allowing the Virtualize code to focus on things like snapshots and flash grid and replication. So that's what makes it different.
Wow. I know it is the case for us and our business, but would you say that most of the SSDs IBM ships in Flash system today are FCMs?
Exactly, 92.4%, Neil. So yes, most of the most of the SSDs that we ship are. Now, I will tell you that we have good relationships with Samsung and Kioxia, and a lot of clients at the lower end, they use 1.92 terabyte or 3.84 terabyte devices, and we start at 4.8. So for lower capacities, that's where we sometimes sell other SSDs.
Yep. Okay. And what's the benefit of doing data reduction inside the FCM instead of in the controller?
Yeah. That's an important question to really get at the bottom, because believe it or not, it's not really about the compressing itself. All right. Although having 24, let's say you have 24 FCMs in your 7300, then you have 24 little offload compression engines that are allowing you to compress at full speed. All right. But the real benefit is this. All right. When you compress data, you're going to end up with less data than you started, right, Neil? So you can't write it to the same place. The host has said, I'm going to write this to volume 7, LBA 12. Well, if you have a deterministic map, you now have less data. You can't write it there, or else you'd have a big space between it and the next. So instead, what you have to do is come up with a data structure to remap the data to somewhere else and combine many pieces that are being compressed all into one. And so you have a set of metadata for remapping the host writes to somewhere else, right? Well, that metadata can be large, but here is another key piece of that. A new write comes in, all right? I'm overwriting data that I already had. So now I've got to go to that data structure. I've got to invalidate what was there. Now I've got to write the new data somewhere else. And as this continues, I end up with a lot of holes in my data structure. It becomes holy. And we're not using holy as a good thing here, all right? Yeah. you have holes that you've got to reclaim. So you have to go through a process called garbage collection, right? Well, garbage collection is an expensive thing to do from the processor, especially when you're doing it in a controller that is kind of above the flash, right? You got to go through the NVMe and then to the SSD. And so the beauty of the FCM and why this works so well is an SSD already has to have a log structured array like this, Neil, because you can't write to flash until you erase it. Therefore, it's used to having data come in and having to invalidate and write it somewhere else. That is done by every SSD. And if I now have it compressed first, I can make that process even more efficient. And that really helps. And so now the controllers, the virtualize, I don't have to have these big x86 engines and a lot of memory and have this other structure to tell me where I've remapped data. So it simplifies tremendously, and we end up with higher capacity.
Okay, so Andy, how does that impact things like system density, power usage, or other TCO factors?
Yeah, that's a great question. If you have this metadata structure that requires you to read from it first before you can write the data, and you've got to do garbage collection, as that thing expands, it's harder and harder to fit in memory. And so you might have larger and larger DRAM, but eventually it becomes so big and unwieldy that the amount of metadata you have is a large percentage, all right? So it limits you on how much capacity you can drive by that controller, all right? And so you end up with controllers that are more expensive, that have more cores in them, that draw more power, and have a limit as to how much capacity they can drive before you have to add another controller, Neil. All right?
Okay.
We can drive in the 9500 1.5 petabyte of usable capacity. That's usable. That's how much can be accessed by the customer, not raw capacity. It's even more than that. And that's in just 2U, all right? And the power draw is very reasonable. So as I do comparisons with other vendors, we draw less power per U, we have higher density per U, and that's the advantage of QLC, along with the offloads that we put into the FCM.
Okay, so I've heard that having FPGA and processors right on the FCM gives us even more advantages. Can you explain that?
Yeah. So an FPGA stands for Field Programmable Gate Array. All right. Probably hasn't helped all of our listeners here know what they are, but just think of them as a large array of SRAM bits. All right. They're memory bits. They're different than DRAM in that they don't need to be refreshed. You load a value into them and they will keep it. Okay. And these SRAM bits then, they determine how you are programming a set of logic tables above them. All right. So you can program the FPGA by setting bits into this SRAM array to tell it, okay, here's an XOR gate, here's an AND gate, here's a NOR gate. You can set up latches. So essentially, you can have the equivalent of an ASIC, a logic device, that you can use to program your design. And so the beauty of that is that with an FPGA, it's programmable. And so let's say, Neil, we find a problem, all right, in the FPGA. I wish I could tell you we never ship any problems, but last time I checked, we're still human. So we make mistakes. And the beauty is, when we do that, we can tell you, Neil, and you can go and download the fix to that, and now it works, all right? And it probably was an edge condition to begin with, so you may not even need it, but we can fix these bugs, All right. That's one advantage. The other is that I can put offloads in that and program it and add offloads as we go along. All right. With an ASIC, you're kind of stuck. All right. It is until you spend another 20 to 30 million to release another one. Now, don't get me wrong, an ASIC is a good thing to do, and we're looking at that as well, but we use FPGAs as a foundation to make sure we get the design right and have all of the other pieces there so that when we go to an ASIC, we still have computational storage because we'll have ARM processors and such. So hopefully that answered your question.
Okay, so is that what people mean when they talk about computational storage?
Well, computational storage is offloading things from the server or from the controller into the storage itself. The compression, for example, and the decompression is an example of computational storage. It is being done there instead of the server having to do it. If I offload things from the controllers in a virtualized system down into the FCM, I'm having the FCM offload the processor. And the reason for it is very important. The Moore's Law is getting harder and harder to achieve. All right. And so AMD and Intel, they continue to do a phenomenal job in putting more cores down, but no longer are you going to be able in 18 months to get twice the compute at the same cost as you did before. It's just not possible anymore. You pay more. I'm sure you see that in your data center. So by having computational storage and moving some of that onto the storage itself, that helps to alleviate or the need for more intense processing up above, and that's computational storage.
Okay, thank you. So something very close to my heart and to my customers is if we can talk about ransomware detection that's built into the FCM. It launched in 2024, right? What exactly does it do, and how does it help Flash System users?
All right. Yeah. I'm glad that it's important to you too. It is one of the highlights of my entire career, Neil, coming up with an idea. And it started probably in late 2022, early 2023, as we were looking at, well, what should we be doing in the future? What kinds of things can we do to differentiate and help our clients? And I had the idea of helping the security and the ransomware, trying to detect ransomware. And I remember people telling me, well, you can't do that in block storage. And Neil, whenever anybody tells me something can't be done, that's a huge motivator to me. And so we went out and talked to a number of ISVs, Epic being one, independent software vendors. And I don't know if you're familiar with Epic, but they're in the US, they're a big healthcare management software provider.
Okay.
And their customers are hospitals, all right?
Yep.
Hospitals. They provide software to hospitals. And I talked to the storage guy, a good friend of mine. I said, Will, have you guys had any ransomware attack in your clients? He said, oh, yes, Andy, 2 to 3 a month. Okay. Wow. 2 to 3 a month. And he said something, Neil, that caused me to focus on this and think it's one of the most important things we can do and the industry can do. He said, Andy, patients have died. Okay. And you look at what's happened out there, Neil, and I'm sure your company is extremely concerned about ransomware. And we can't just rely on the edge, can we? It's important. We need to keep doing the edge. And I'm not, they're doing phenomenal, but somewhere somebody's going to answer a phishing software and they're going to allow somebody to get in, aren't they, Neil? Despite our best efforts. So
absolutely.
Once they get in, let's have the storage device like us have the training, and we use an AI model. So the FCM is looking at statistics that we gather every 2 seconds, Neil. We're gathering the average entropy, the delta compression, read-write ratios, all of these statistics, and sending them up every 2 seconds to an inference engine that's running in Virtualize, on a core in Virtualize, and it's been trained by AI. And it now looks at everything coming in, and on a given window will say, okay, I've had enough votes here for a ransomware thing going on that I'm going to raise an alert. Okay.
Yeah.
And something that we did, that I came up with really just before the release, that I'm so glad I did, was we said, okay, every time an alert is raised, we're going to send an hour's worth of data back to SI, to Storage Insights. Well, that means I have an hour's worth of statistics that I can use to train the model and help my false positive rate. Because you probably know the false positives are the enemy of things like this. If I give you enough of them, Neil, what will you do? Just stop looking, right?
Yes.
And we have improved our false positive rate. We keep training for new types of ransomware. I don't want to say what they are because I don't want to give hints to others that we are, but we stay on the latest and make sure that we continue to inject ransomware, and we have a great ransomware simulator so that we help you in your job. You know, it's an attacker's already got in, but if I can find it quickly, that helps you in recovery, right?
Yeah, definitely. And it's so important to us and our customers. It just gives that peace of mind.
Yeah.
So Andy, what's your broader vision when it comes to security and ransomware protection? Where do you see that going?
Yeah. It's one of those areas I love to think about, love to innovate. And so we continue to have ideas of how we can have additional ransomware models that we run on, like GPUs, Neil. And I won't give details as to where the GPUs might be, but imagine having a GPU in the flash grid, in the flash system grid, or somewhere that can do more than just one core on a virtualized. And imagine also looking not just at corruption like entropy and other types, but a key is, what about exfiltration? Looking at exfiltration, as you know, that's one of the biggest worries. And again, I was told you can't find exfiltration in so all right, great. That's where we're going.
Yep. Right.
And sure, these things are hard, but let's focus. And not just IBM, let's focus as an industry. And the great thing about IBM is it's not just the FCM, it's not just this. We also have Defender, Neil, that is there, that is also working, and we work together. And that's the beauty of what we need to do. Every piece of the stack has to do this. The FCM is not enough, Neil, as you know. It's not enough. Everything has to work together.
Yeah. And I love this focus. I love that IBM is taking this full stack approach. Storage Insights, amazing for the customer to be able to look at that data, interpret it, and action what happens next. I think it's all brilliant. And while we're on the topic of the future, what's next for FCM? What can we expect down the road?
Well, I want to be careful in answering that because it's important not to give too many hints. But let me just say that the beauty of having that FPGA and FCM4 is many of the things we're talking about here for the ransomware detection and stuff we'll put into the FCM4, Neil, and it will keep going and such. And so it's important to us that clients who buy the current ones can keep using it. So I really encourage. They're still extremely relevant to today. But obviously, flash continues to advance and the density continues to increase. And so you can expect in the future higher density FCMs, and you can expect higher density virtualized systems as a result of that. And we want to keep working on our data reduction and improve the data reduction. We get good compression, but we want to keep looking at that. So these are some of the areas along with that ransomware detection.
Yeah.
How's that?
Brilliant. I certainly see these things shaking up the market already. The higher density stuff is really working for us in our business. So it's great. Really looking forward to it. So just, I thought you retired. What brought you back?
Neil, there's an interesting anagram to the word retired, taking the letters retired, and it's retried, right? So
yep.
As I was looking at retirement, first of all, IBM was really nice, and they said, we really still need you, and know that you want to retire, but boy, it'd still be nice to have you. So I thought, well, let's just form this LLC. Let's form Great Walls of Storage, and I can keep working and innovating and working with the team, helping them to continue to grow. And I keep my brain occupied, I keep, and my wife actually thought this was a good idea. Well, I think part of it was, I don't want you here all day long.
Brilliant.
And it's really a good ease into retirement, and I've enjoyed it.
Yeah, that's great. And it's so good to see you around, and your positivity and your focus is always appreciated.
Oh, thank you, Neil. Good luck to you.
Thank you very much. Thank you, Andy.